Hello everybody. In this video, we are going to be the guided practice for chapter number 5. It's going to be a really fun one. We are going to install importing scikit-learn and start using it, and we'll use some of those base and datasets that it already has so we can proceed and working forward. So please follow along. So what I just did, I already uploaded everything from the guided practice to my Google Drive. I opened the Jupyter notebook and it's already open in my Colab. So I'm ready to start. Let's do it. Sorry for that. So the first thing this action is to do is to import datasets from scikit-learn. Then we'll use the load iras, access the describe attribute for the iras object and print it just to see where it actually came from. So let's start doing that in the first line. So something that I would like to use right now, even that it doesn't say there, it's just good practice to do it one more time. Just do from Google.Colab. Let's do import or drive, and let's do drive.mount. Let's do our content drive, right? Oh, just to have it there mounted already. And of course, you need to mount, okay? So now we can actually do the practice. Let's do from scikit-learn. That's the way it's called. We need to import datasets. And then we do iris will be the data set, and we use the load iris function to put it in memory. And in order to see what is there, we can do as simple as print iris.description, describe, and that should be it. So let's run it. Let's see where it came from. So we need to wait. It will take a little bit longer. Uh, of course, I had a typo here, so it's actually drive.mount. Give you permission. Yes, let's connect to Google Drive. Let's continue. Continue. And then we will import the datasets, load the iris one. I have another typo right here. So this actually should call iris. Let's just stop it and run it one more time. It will probably say an error that my drive is already mounted, but let's see. Okay, somehow it failed several times. I just closed that part of the video. So what I added for drive my mount point is just added force remount true. So it looked like it was mounted, but even that I was not able to see it somehow, but it was there. So when I do force remount equal true, it just work and went through it. So if you have issues, you just add this part and it should work for you. Okay. So we import the dataset here. So we import the load iris and we import the describe. And we can see pretty much what it has. It gives you the attributes information about sepal, the petals, the class with Statosas, versicolor, and virginica. And we can see the width, max, means, size, class correlation, and some description information about that particular one. So the idea here will be now that it's actually loaded, we can start working through that. So we can access the features names and the iris datasets. So feature names, we see that are the attributes in the dataset, and those are represented by physical characteristics such as sepal length, sepal width, and the petal width. So, and then we can access the target and the target names too. So we can actually proceed to seeing those right there. So we can do as simple as print or iris that is already set up, and let's do our feature names and execute. And we can see that we have sepal length, sepal width, petal length, and petal width. So with that features, we can follow and start doing some elements. Let's see also the targets and the target names. That we can have those. So we should be able to print just our item dot target and print our iris target names. With the T here. So you can see the values that we have in our target is 0, 1, and 2. 0 belongs to setosas, 1 to versicolor, and 2 to virginicas. So now that we have those datasets in, we can start converting those datasets in pandas data frames that we'll be using later in our application. So we'll do as simple as import pandas as PD, and we can do our data frame will be our pt.data frame, and we need to set up the data, so we'll use the iris.data, and we can print the head the way that it's asking us here to do. So let's do print or data frame head, and let's see where it came from. Cool. We can see that the different versions and values is right there working with the first 5 rows of the data frame with the head method. So we can see the 4 different columns that belongs to our sepal length, width, petal length, and width right here. And then we have the different rows, the first 5 ones, and provide the data that we have. So now we can start plotting and weighting using Matplotlib. So let's see how everything is set up here. So, well, instead of doing that, let's do plotting weight and height and weight. So let's just define a data set that will be a custom one. We can invent it. So let's just work on those. So we do the matplotlib. We do the title, the label, the plot, the K, and the axis and the grid. So we can start working with those. So of course we need to import matplotlib dot pyplot as plt mat, and I have a typo, of course. Matplot, come on. There you go. So we can have a couple of data sets. I already have those. So let me just import those right here. So I just random all the way 5 to 6 across the board, on different weight. And we can do now, let's do plt.title. Let's make this to be heights versus weight. Let's do the X label. My X label will be, let's do height in fit, because that's what we're providing. And my Y label will be weight in pounds. The next thing, let's do the plt.plot. So now what we actually want to see. We want to see our height, or weight, and let's use the k dot. So that's the dot plot scale system. Actually, k dot. There you go. Let's do the axis with I. And let's do, for example, I don't know, 4, 4 and 8, 6.4, 90, and 200. So we are just keeping a little bit more inside these boundaries. From 4.9 is below 5, 6.4 just a little bit up, that's 6.2, 90 all the way to 200. And let's do for now the plt dot grid as true. So we can see the little lines and the square lines in the plot, and we can show it. And let's see how this actually looks like right now. Oh, yeah, I'm providing, this actually should be an array. So I need to put those as a list in the array. And let's try it. There you go. So we can see the line is right there. We can see how it is going to be the height with the weight. And now we can do the linear regression with scikit-learn about how to recreate that relationship that we have here. So let's do the following. We need to, from scikit-learn linear model, we need to import our linear regression, right? Then we can do, we need to provide our x and our y. So x should be a 2D graphic for scikit-learn. So the x, it will equal to h for every h in height, and y will be for weight. So we do model equal linear regression, we just call it, and the model dot fit x and y. And this should be dot fit. So how do you like it? Ah, there you go. Just remove it. So now with that, we can just print the slope and the intercept to see how those actually look like here. So to print slope, and we can also print our intercept. And let's run it. Ooh. Oh, missing the comma here. Yeah, 75, and the intercept minus 275. This is really cool because that means that it found a math formula that pretty much it says, oh, the way that we find is that our weight is equal to 75 multiplied by our height minus 275. Mostly, right? That's the formula that I found through that linear regression about the data set that we provided. So we can do the predict code here. So we can do something like height to predict we will equal, let's do 5.74. That's the one that we want to see who actually do. Let's just make it this, let's keep as it is. So 574. So we can do predicted weight will be equal or model dot predict with our height to predict. That will, the model will try with that input and with the data that it has and the correlation that it found, try to predict what weight somebody with this height should have, right? So let's just round it because probably it will be a really big number. So let's put it like rounded weight. Let's just round this the predicted weight. There you go. Actually, predicted. Yeah, I have it wrong here. Let's change this one. So let's round it so you don't have that many zeros at the end. So it will keep it slow, and we can just at least print those two and tell you know what? Print the way for 70, 50, 74 will be the rounded way that we just have. And let's see. So he predicted that somebody with this height, it should be around 155 pounds, more or less. And it's good or bad. Remember, every model will be as good as the value of the data and the quantity of data is going to be trained. So we just train it here with just a couple of them. We just train it with 7, 1, 2, 3, 4, 5, 6, 7 different ones. So based on the data that it has, it can predict that somebody with 574, it will weigh 155. If we go back to our plot, the 574, it will be around here. So if we can see that correlation, it detects that it should be around here. Because 55, it will be in the middle, goes a little bit up. And you can see that my arrow is actually aligned with those particular dots because it's aligned what I just have here. So it just did what it's supposed to with a simple linear regression. So what we can do now is just plotting regression lines alongside data points. And we'll see if the predictions and the data points actually, how they actually look like together. So let's do import matplotlib the pyplot as plt, and we do x will be age for age in height, and we can do predicted weight in plural will be model dot predict or x feature full, and let's do a couple of labels and titles here. I just put it here with let's do title regression line alongside data points. Label in X will be height in feet. Label in Y will weight in pounds. And let's just plot that in the official one, the height and the weights that we have. But also, let's plot a second line with color R, red, or heights with the predicted weight. So let's have the two lines, well, the dots of the real ones and the line for the predicted one. And let's just do the same axis that we have, and let's do the grid and show the actually matplotlib. And we can see it right there that is predicting in that particular line. So when we ask for 574 across here, it will be pretty much here. That it makes sense that it's between the half part and 160, so that 55 is right there. So we can see that the line that it detects for the predicted weight, it goes through the data points that it got trained this particular model, right? So let's calculate the residual sum of squares to measure the discrepancy between the observed values and the values predicted by the linear regression. For that one, let's use NumPy in this particular area. So let me just put those right here. I'm going to import NumPy as NP, and we can make predictions. With a predicted weight will be the model that we have, or we can just keep it as it is, but let's through it through here. And residual will be n by array weights minus the predicted weight. Let's see how that actually works. Square residuals will be residual at 2, and errors will be the sum for those square residuals. And let's see how it actually looks like. Right there, we can see the residuals are minimal. We see this is a 5.6, the exponent minus 14 is just really, really small data set with the RS00. That means is pretty much predict exactly those values because that's pretty much the data what it got trained. So we can see those is actually exactly those. So because the values that we provide before are really linear, we can see those right there. So let's make some changes here so we can see a difference. So I will comment this out and I will create a new height and weight that is similar in a way but have different weights. So it should have a little discrepancy all over the place. You can see that it's not look like a line now. It looks a little bit different there. So when we do here, the slope and the intercept is just a little bit different too, because we have a different data set. So when we predicted 574, it will should give us a 1 more pound. Okay, so let's try to see the new ones. Now we can see that the line, it goes really near the points that we have, but now it doesn't touch those right there. That means that our RSS should be now different. It should not be a zero because we pretty much have the residuals at zero. So we can see there it's a 43.86. So we can see right now the residuals show how far each actual weight is from the weight predicted by the regression model. A residue is calculated like this: actual weight minus predicted weight. That's pretty much what we have here. The actual weight minus the predicted one. And this positive residual means that the actual weight was higher than the model predicted. That means the prediction is goes below what is supposed to be or what the actually values has in the actual weight. If this was a negative, that means the predicted is actually bigger than the actual real value. In our output, the residuals are small numbers like 2.64 minus 286. That means those models predictions are only off by 2 or 3 pounds for each data point. And we can see right here. That's how long up and down it has. So the residual sum of squares is 4386. This number measures the total error of the regression model. We square the residuals, so negative and positive errors do not cancel each other out. A zero means the regression line fits perfectly. The 4386 that we have now, the line is close to the data, but not perfect. So we can see with different values of within data, it actually provides different elements there. So let's now pretty much calculate the R square, the coefficient determination, and the value of 1 to 0 to 1. Indicates that the model perfect predict if a 1 is a 0, then the model does not explain any of the variance in the data. That means it's really far off. And we can use the dot score to actually see those elements. So we can do as simple as R square. Let's do R square just to see how well or bad our model is doing. So let's model the score for X with or Y's. And we can, as simple as print, and let's round it so it doesn't have that many um, 0 points. So let's do square and let's just do 4 for now. So we have a 0.9935. Tell us how well the regression is because really near 1, that means it's actually doing a really good job because that 99 means that it's predicting in a 99% correctly what it should be doing. So it's doing pretty well with the value of the data that we just provided. So let's check any missing values. Let's verify if those actually doing something. It's null is a method used to detect missing values in a data set and return the data frame in the same shape. Yeah, so let's provide those. So let's do something really simple here. For make this work, so we'll use the not as number data set. Let's bring it up. We have some not a number there, so we can actually review what those look like and what we actually have here. So let me show you how to do it. So remember, we just import pandas as PD. Data frame will be PD read CSV, and let's provide that for our content drive, my drive, and I call my folder CTP3304, CITP3304 forward slash, and let's do it not a number dataset dot CSV. Cool. So we import it. Let's print it, the data frame, and let's see how much nulls we have here. So it's null, and let's summarize those so we can have the value the way it's supposed to. And this is not in here, it's like this. Cool. So we use for pandas. And this should be this. I'm sorry, this is a function. Cool. So this is our data set. We can see you just have 6 values there. We have some nodes and numbers right there. In column B. So we can see that our null gives A doesn't have any null, B has 2, C has 4. This data set contains missing values in that column B, right? That's the way that we need to see it right now. So we need to replace those and those values. We fill those not a numbers method, and we use the mean in order to provide and fill the missing ones. So let me show you how to use the data frame with mean so we can change line 1 and 2 with the mean of what that column actually has. And later we can drop it. Also, we'll drop NA and we show that how that actually looks like too. So let's go through here and let's do it really simple. So let's, our big column is going to be equal our data frame from B. And we just need to fill not a number with something with a value. So let's do fill it with the mean function that it provides us pandas with the data frames elements. And we can just see now print or data frame. And this is data frame, not DB. And let's see it. And you can see now, instead of not a number, we have 11 there. Because that's pretty much the mean value that we have crossboard. So that's one way to utilize those in a way that provides us that information. Now, let's drop in the rows with the missing values. And let's see how those actually look like now. What we can do right there, let's just reprint because our data frame is already changed. Let's go back here and let's read that one more time. So that way we can have our data set reset in a way. And now we can do simple as our data frame equal drop not the numbers. And we can do a simple as printed. And here we didn't define a specific column, so we just do, and it's actually data frame drop a number. And we can see that values that it has not a number are not showing here. Let's do another print before, so we can have one before and one after, just to see those. So actually printing the same way. So let's do, well, you can see it right here. So this is our original one. We have 4 and 7 with the numbers in B. So 4 and 7 are not existing anymore later. before it's actually doing the process of removing those. So one thing that it just happened because we just dropped the not numbers, you can see our indexes actually messed up. So we had before 0, 1, 2, 3, 4, 5. We have 0, 3, 4, 5 because 1 and 2 just got deleted. So Pandas give you the reset index with drop through. We set the index of the data frame again. So we can use a simple data frame will be our data frame. And we can do reset index. And let's do from drop equal true. And then we can just print it. And we should be the same data set, this second one, but with the correct index, as you can see right here. So it goes to 0 to 1 instead of 0 to 3, the way that we had it before. And now we have the index working the way it's supposed to. Let's do another data frame that we have. We have the duplicate rows. Let's import that. And we just define the duplicate keep false to identify which one is duplicate or not. We can do something as simple as importing the dataset. And after we import the dataset, we just need to print which one are duplicate. So let's do import pandas as PD. And then the data frame will be PD read CSV. And let's actually get all this. It will be really similar. But instead of non-dataset, let's actually do duplicate row. If we just print that data frame, let's see what it have. We have, this one is unique, but we can see that 1 and 2 actually duplicate. It has the same values. We can see that 5 and 6 are duplicates too. So one way or one method that we can utilize here, let's do print some line just to have a division there. And let's do print, let's do duplicated. And let's do the keep equal false. True indicate the row is a duplicate, false indicate the row is unique. Keep false marks all occurrence of duplicate as true. By default, keep first will mark only the subsequent duplicate as true. So right now it's just to have everything that is duplicate as a true. We can see right there that 1 and 2 are true, and 5 and 6 are true. So if we change the keep to first, we only mark the second instance. So we'll keep this one, and the second one will be identified as an actual true. So let's actually see it. So let's get this and let's put it here and change this to first and run it. As you can see, now the real duplicate, keeping the first one as false. And now the first duplicate is the one that is identified here. But what that mean? That means that we can actually do also last. And last, what it do, it mark the last one as a false and the first one as a true in duplicate. So 1 and 2, only one, and 5 and 6. Sorry, which one? I remember which one we are. We had it here. 5 and 6. Yes, 5 and 6. The 5 is the one that is true because the last one keep it as a false. Because now that we have that identification, we can just display in the one that we needed in a particular way or even remove it later. For that, we can just copy this one over here. And let's see how it shows. We can see now keep feedback false with the df. We can just keep the one that are duplicate per se. Just give me 1 and 2, 5 and 6. That way we can just see the ones that we require in this particular element. So we this is our selector for the data frame, and that's the way that we should have it through here. Having that, will be very beneficial for us because now we can change the data or manipulate the data in a way that remove or adding elements the way that we need it. So let's just execute that, showing dropping the duplicate rows. So let's use the keep first. That means the first will be sent as a false. And when you do drop duplicates in place true, that means we're doing true the data frame without needed to equalize it somewhere. So here is just telling change the data frame. That's what I'm telling. The in place true are when modify the original data frame without returning a new one, because so far we'll be doing here is where is the previous one? Here, drop not NA, it just give us one before, right? And we just override the data frame because it give us a copy of those. So that in place will do it without needed to returning. So we're just changing the original here. Let's print df, and now those duplicates are not there. And you can see that our indexes are messed up again because just remove the duplicate row the way that we had it in our dataset. Something extra that we can do is actually really cool is normalize columns using min max scaling. So sometimes our data frames or our values, some are scored in the thousands and the hundreds, in the 10,000 millions even, sometimes just in ones and twos. So when we try to do correlation, it looks like they're really far away. So we need to normalize it in a way that will ground their information in a concept like percentage, let's say like that. So if we have a scale that is 1 to 10, when 10 is will be 100, if we have a scale of 1 to 1,000, 1,000 will be 100 too. So that will be reducing and keeping those in a way that will tag to each other in the same values. So we can use here import pandas as PD, and let's do from sklearn, let's do import pre-processing we will be using here. For now, let's do our data frame will be our pandas read CSV, and let's just get the normalized columns. Let's copy path. Probably will faster. Let me remove it from here, and I will just put it right here. And let's print it so you can actually see what we have right now. You can see column A is really a lot bigger than column B and C in the current file. So let's normalize this or in values that will be from 0 all the way to 1. And we can use pandas to help us define those particular ones. So let's do, for now, let's do print. Let's just have a line so we can identify it, the previous and the later one. And we can do, let's do variable X will be our data frame values. And we can do the as type. We define what type they are. Let's do float, not do the calculation. And we can now have our minimum, maximum scalar to play around through the pre-processing that we just already imported. And we use the min max scalar. So that will be the scalar, that will be the values that will be defined as number, right? And now that we have those numbers float that we needed, we do the data frame will be now my panda data frame or scale, and we'll call columns. Will be my current columns that I have, right? Of course, I'm missing here something because I didn't define what is a scale. Scale will be my min max scalar. That is the pre-processing, and will be, you know what? You need to fit transform that we have right here, the fit transform, and we'll transform our x, that is the values that we have as float for the previous data frame. Cool. Now that we have the scale it, it should be scale it. It should not complain anymore. I don't know what is complaining now. Oh, because this is not equal. Let's see. There you go. Perfect. And now can just print it one more time. And let's see how that works. So you can see the original values and the new ones are from the range from 0 all the way to 1. So now they're actually talking the same language. You can see that the maximum value on A is 1600. So 1600 to get the 1. Maximum value of B is 17, and that's the one to get it as a 1. And the maximum value of C is 18, that's the one to get as a 1. That's the way that it do the correlation about with the minimal maximum scalar. And now that we have our data frame in the same level, we can do elements through those particular values. So let's move along. And let's now do the Z-score method for outlier detection. So Z-score is a measure to describe the value relationship to the mean value, and it will calculate through the Z-score, and that is X is the data point, and the U is the data set, and the sigma is the standard deviation of the data set. So it's pretty much like X, the data point, minus the mean of the data set divided by the deviation of the data set. And that is considered an extreme outlier finding, and typically a data point of Z-score greater or less than 3 or minus 3, it will define that we have an outlier. What is an outlier? It could be something that is right out of the scope. Let's say, for example, I'm grading everybody, and then I have all my grades from, let's say, from 80 to 100. And we have a couple of 70s there, but let's say by error, somebody that it has an 80, I just put an 8 there. And let's say somebody that instead of having a 90, you have a 900. Like I have a typo, I'm missing a 0 in one, and I have an extra 0 in the other one. For those, what it will actually happen, the Z-score will actually detect if I have the really big list of everybody on the class, it will detect, so you know what, that 8 is actually too below, and that 900 is actually too up. So it's a way to detect those scores and determine which value does not belong or is not grouped inside, and it find out as outlier in the system. And for that, we are going to do um, uh, how can I say this? A function, sorry, I just lost the name. Let's do a function that pretty much do this, so we can call later and determine the outlier using the Z-score, and we use the Galton dataset for that. So let's just create this function. It's really simple. Let's do define outliers with our Z-score. And I know that is complex math, but don't worry, I will provide that for you guys. So let's do a threshold equal 3. Let's do a mean. It will require numpy, so let's do np.mean for the data. Let's do the standard deviation. Will be numpy.standard deviation from the data. Data will be the element that will be sent to the function, of course. And then we can do the Z-scores. It will be pretty much our step here and let's do or y mean y minus mean actually divided by our standard deviation for every y in our data, right? So let's just keep it this separate so it will be better to read. So it will be y minus mean divided by standard deviation for every value in our data that will be identified as y. And just return from NumPy, we can just tell where np.absolute, and we can do our z-score is bigger than our threshold. So y absolute because we need to define the -3 and the +3. So here we just change it to an absolute, so everything will be positive. And if that threshold is bigger than 3, that's where we just return it to our NumPy function. Let's run this. It will not provide any output, but will define the functions that we'll use at the end whenever we import now our Galton information. So let me get this. Let's do copy path and let's follow. So let's do import pandas as PD, import numpy as np, and let's do our data frame will be panda.read CSV for the Galton. Let's just print it so we can actually see it, what it has there. Right? It have 898 lines, rows, 6 columns. We can see the resume here. And we can see the values from family 1 all the way to 136A, 70, and we can see the sex and height and how many kids, right? That's information that we have. So let's find those outliers. Let's do it through here. And we can do a simple for loop. So let's do for, let's do index, because we're going to get in our outliers z-score, and let's send our height element to provide us which one is an outlier in this particular element. So for index in outliers for the height, we can just print index. You will see it's also giving us which one do we need to print. So because we have those right there, we should be able to just print our data frame, and we'll say I want to print that particular index and finish index. And the last one, oh, do you know like the range in Python? You say when it begins and when it ends, but the end is not inclusive. Let's do a simple index plus 1. And we should be able now to see those right there. It's not liking it in a way. So I'm telling them to print what is missing, what I have an issue here. Print or data frame index to index plus 1. Looks good. So probably I'm doing something that I should not be. Oh, wait. I need to print, yes, the first one because it gave us an array. So I tell them, give me the first element for this list, for the outliers. That's what is happening there. Cool. Cool. So now I can see it give me the 125, 120 to and 672. That we found those heights as outliers according with the value that we have across the board. So now that we have the outlier percent that are just too big or too short, we can just make a separation, remove those, have the mean, or any value depending the data that we want to provide. So this is just a way to calculate those before we actually do a specific value. So far, I hope that you like it. I know that was a really long video. I think we are about 50 minutes recording. So recap, we're able to import the dataset and see what the dataset has. We'll be able to see the features names, target and target names that came for Sigland already. We create our Panda dataset from that values that we imported. We're able to um, print some height, weight, and we have the correlation, really linear, a little changed, and we're able to calculate the linear regression of those values and write to the predictions. And later we'll be able to plot whenever it was inside the prediction or whenever they are a little bit outside to calculate the residual sum of squares, even of 43, and then calculate the R square of 99. That is really, really good in this particular area. We'll be able to see data set where we have null, not a number values. We'll be able to change those to the mean, remove those, change those to the mean, or change or actually pretty much drop it. Then we were able to understand when we have repetitions. This we're going to select those duplications and then drop those duplications, show them and then drop them the way that we need it, and we did it in place to normalize our data when we have really big ranges across the board. So you will learn later, learn how to do a better calculation because everything is normalized in the values that it understand. We find out the complex math for the Z-score, and we just do a quick, simple function that does that for us. And we're able to import data from Galton and find out those outliers during that. So I really hope that you like it. Please follow up and print the PDF of this file and do also the other one. So meanwhile, if you have any question or any doubt, please don't hesitate to reach me. Happy coding, everybody.